So this video is going to calculate the volume of a sphere in every way we know how. So starting with single integrals, going through double integrals, and all the way through triple integrals in all three of our formats: rectangular, cylindrical, and spherical coordinates. And the point of doing this is when you get a new skill, like triple integration, it's good to know how to do problems and to be comfortable with a new skill, but it's also good to put it into context. And like I said, triple integration can find volumes. It's not always good for finding volumes. It's not always the best way. So you'll see that, and you'll see when we do problems that don't have to do with volume, it may be the best way, or it may be the only way. But here, actually my personal favorite is just the disk method for finding volume of a sphere. And we'll see that shortly, and you'll see the other ones, and you'll be able to compare them all. I'll try to do some of these quickly since you hopefully know these pretty well. I've known these for a while. And let's just remind ourselves that the answer to the volume of a sphere should be 4/3 pi r cubed. We know that from geometry. And in fact, every single one of these approaches is a proof of that fact. They didn't prove it to you in geometry because you didn't know any calculus yet. Okay, so let's look at single integration. And back in this course, either Math 125 or wherever you first learned about integrals, you called these volumes of revolution. So the way you got a sphere in this course, because you were stuck in 2 dimensions, is you had a circle, or probably actually just a half circle of radius r. That was r, and then you rotated it about the x-axis. And then the equation of the top half of the circle is y equals the root of r squared minus x squared. Okay, and so then you had the disk method for finding the volume of that revolved surface, which is going to result in a sphere. And we sliced that sphere up into disks. Okay, so this point here was the point x comma the root of r squared minus x squared. So that radius of that disk is the root of r squared minus x squared. So you integrated, x went from negative r to positive r, and you had the area of the disk was pi r squared. Pi r squared is just r squared minus x squared if the radius is the root of that. And then the thickness of the disk was dx, and you added up all the thickness of the disks and you got your integral. Okay, so let's do this quickly. Let's see, we can just integrate, right? This is pi r squared x minus pi x cubed over 3 as x goes from negative r to r. Putting in r, we get pi r cubed minus pi r cubed over 3 minus, but then we're putting in negative r for x, so it actually turns out to be plus pi r cubed, and then we have minus, and we have this minus sign, and we have a negative r cubed, so there's an odd number of minus signs, so that turns out to be negative pi r cubed over 3. And each of these is 2/3 pi r cubed, so we get a total of 4/3 pi r cubed. Okay, so that's not hard. When I do that, I don't feel like I need more technology or a better method. And in fact, I don't. That's a perfectly good method. That is, in fact, my favorite. They gave you another method in 125 or your first integration course. Sorry, not shell integration, shell method. And that was same thing. You had this curve, y equals the root of r squared minus x squared. You rotated it about the x-axis, but now we took cylinders or shells, and you had, tall skinny cylinders that made up your sphere, and then as you got more towards the center, we got shorter, fatter cylinders. Okay, so we need to add up the volumes of the cylindrical slices, the shells. This time we're only changing x from 0 to r, because that's where you get all the shells. Okay, so we go from 0 to r, and then what do we need? We need the surface area of the cylinder times the change in thickness. So thickness is dx, Surface area of the cylinder is circumference times the height, because you can cut it out and roll it out into a rectangle. So circumference is 2 pi x, right? If you look at any given cylinder, then the radius of that cylinder is x. And then the height is double the y-coordinate of that point. So x comma root r squared minus x squared. The height of the cylinder is double that value. So we're multiplying by 2 root r squared minus x squared. Okay, and then we just need to integrate that. We'll do that quickly. This is a quick u substitution. If we make u equal to r squared minus x squared, then du is negative 2x dx. So 2x dx, not 2dx, 2x dx is minus 1/2 du. Oh no, sorry, not my, I can't have a 2 and a 1/2. It's just negative du. Okay, great. So what I'm doing is I'm replacing the 2x dx with negative du. So I still have a 2 pi, and I have a negative 2 pi. I'm integrating as x goes from 0 to r, and then I have the root of u du. Okay, so that integral, negative 2 pi, I'm going to get u to the power of 3/2, adding 1 to the exponent, and then dividing by that exponent, I get a 2/3. X goes from 0 to r, and then I sub that back in, so I get minus 4/3 pi. That seems promising. R squared minus x squared to the 3/2, x going from 0 to r. Putting in r, I get 0. Putting in 0, I have minus and negative again. So I have positive 4/3 pi r squared to the 3/2, which works out to r cubed. And I don't have to worry about sign because r is the radius, so it's positive. Okay, so same answer, so that's good. I think this way is a little bit harder. So that's fine, we can do it. Just keep track of that. Then you moved on to Math 126, and we could do this with a double integral. And then how did we do this with a double integral? Well, we knew how to get the volume under a surface. We just integrate up to that surface. Let the z go up to that surface. So here's the sphere. And then the top half of the sphere was z equals the root of r squared minus x squared minus y squared. The bottom half of the surface was z equals negative the root of r squared minus x squared minus y squared. So two ways you could think of this. You could integrate over your region, and we could do the top half minus the bottom half. Dx dy, or that's the same as thinking about it as just saying volume under the top half multiplied by 2. And you'll see like these, that will be minus a negative is a plus, so it'll work out to be the same thing. So 2 times the integral over the region r squared minus x squared minus y squared dx dy. And then what is that region? Well, that's a circle in the xy plane, circle of radius r. Okay, so if we tried to do this in rectangular coordinates, we would have x going from negative r to r, and then same issue, y needs to go from the bottom half of the circle, which is going to be negative the root of r squared minus x squared, to the top half of the circle, which is the root of r squared minus x squared. Then this is pretty ugly looking. And okay, y now goes on the inside because these are the bounds for y, and x goes on the outside. Okay, great. I don't know how to integrate that. Right? I don't know how to integrate the root of something minus y squared with respect to y. Maybe I could. It's hard. Trig substitution might work there. Or, polar coordinates is just a substitute for trig substitution, basically. A little bit easier to think about. Okay, so how about we integrate in polar coordinates? So 2, we'll worry about the bounds in a second. This root is good. That's the root of r squared minus little r squared. because little r squared is x squared plus y squared. Great, we have an r d theta out here. That already looks good because now with this extra r term, we can probably do a u substitution. And then we're still looking at that whole circle of radius r. Okay, so that's good. So little r is going to go from 0 to big R, and theta is going to go from 0 to 2 pi, and that'll get you that whole circle. Okay, that looks a lot better. This looks a lot like shell method, right? After, oh no, even before we did the u sub. It's just we didn't have the theta. That 2 pi actually accounts for the integral with respect to theta once we do it. So make a note of that, similar to shell method. It was possibly a little bit easier to set up. We didn't have to think about cylinders, so there was a little less thinking, but there's more integrals, more notation. So here's that theme where we're trading thinking for notation, and that could be good or bad. It's okay to prefer either one. Okay, so we'll quickly do this integral. It's a u sub, so u equals r squared minus little r squared, which means du is negative 2 little r dr. We can take that 2 in front with it, so 2r dr is negative du. So we got to pull that 2 in. Let's see, integral from 0 to 2 pi, integral from 0 to r, the root of u. We have a negative sign, du, d theta. This is little r going from 0 to big R. Okay, then we'll integrate 0 to 2 pi. Leave that negative there. This is going to be u to the 3 halves again, so we'll have a 2/3 out here. And then we'll have little r going from 0 to big R. We still have to integrate with respect to theta later. We can plug back in. Negative integral from 0 to 2 pi, 2/3 big R squared minus little r squared to the 3 halves, r going from 0 to big R, d theta. Plugging in big R, I get 0. Plugging in 0, I have minus and negative again. So I can get rid of that negative, 0 to 2 pi. Let's see, we get 2/3. And then we have r, big R squared to the 3 halves, which is big R cubed. d theta. Great, that is 2/3 r cubed theta. Theta going from 0 to 2 pi, which is going to be 4/3 pi r cubed. Okay, so we still get the same answer. I don't know that this is getting easier. This is more writing than the previous one. You could argue it was less thinking than the previous one, so maybe it's about the same as the shell method. I would say that might be true. I personally might prefer the shell method over this. Doesn't matter. Okay, and now we're going to do this sphere thing with triple integration. So let's see what's going to happen. We integrate, it's going to be 1 dz dx dy dx. Go backwards, that'll probably be the most intuitive, but it doesn't matter what order you go in necessarily. And we can switch the order later if it's not working out. Okay, so we have a sphere. Let's see, z is going from negative root r squared minus x squared minus y squared. So this is the same theme that we saw before, to positive of that. Right, all our z values go there. And then our y values are going, let's see, x is going to go from negative r to r, y is going to go from negative root of r squared minus x squared to positive root of r squared minus x squared. Okay, and then we integrate that. This is going to look a lot like, after one step, this looks like the double integration, actually. Right, because if I integrate 1 with respect to z, I get z. I plug in these bounds, I'm going to get exactly this expression. that we got up there, and then I integrate with respect to x and y, and I can't do it except maybe with trig subs, so I switch to polar. Okay, so what happens then if we start with cylindrical right away? Is it easier or harder or the same than if I started with rectangular and switched to polar? Okay, well, let's think about that. So what region am I integrating over? So now I have r and theta and z. So now I still have 1. I have dz, and then I have r dr d theta, right? D theta, dz. And then z is probably going to depend on r and theta, so actually I'll put dz on the inside. dz, dr, d theta. And I want to integrate over this whole circle, so that means theta is going to go from 0 to 2 pi. Little r is going to go from 0 to big R. And then what happens to z? Z goes from bottom part of the sphere to top part of the sphere again. Bottom part of the sphere is the root of big R squared minus little r squared. So it looks just like this thing up here, except we've replaced x squared plus y squared with little r squared. And then top half of the sphere, sorry, I shouldn't write in highlighter, is the root of big R squared minus little r squared. Okay, great. And then after one step, it looks like where we got in our double integration, after converting to polar. So maybe we saved a little bit of overhead up front by just thinking about this in cylindrical, which is basically polar. But if you did one step of that integration, you would get to this step here. So that's all the same, basically. No, I don't know if that's better or worse than double integration. I like double integration probably a little bit better, but again, that's not necessarily a strong reason for that preference. Okay, what if we did this in spherical coordinates? This should be really nice because we're finding the volume of a sphere. This feels like it was made for this. Let's think about that. So we need to do a triple integral, and then we have 1 times, and remember that that thing we had to multiply by the end, at the end is pretty ugly. So it's rho squared sine phi d rho, should probably memorize this, d phi d theta. Okay, let's see, spherical coordinates. So rho is going to go from 0 to r. Phi, the full range of phi, right, let's see. Draw axes, full range of phi, it starts at 0 at the z-axis, goes all the way to pi, right? So phi goes from 0 to pi, and then theta goes from 0 to 2 pi. Okay, so this seems nice. Take all values of phi and theta as rho goes from 0 to r. Okay, so we'll just integrate this. Hopefully it's easy. 0 to 2 pi, 0 to pi, we can't touch those yet. Integrate with respect to rho. That's going to be rho cubed over 3. We still have the sine phi hanging out. Rho has to go from 0 to big R. We still have this d phi, d theta. And we'll see later, it's a little bit naive to just go from inside to outside. Here it doesn't matter too much. But sometimes it will make a big difference what order you integrate in. You could make the problem a lot easier or a lot harder. Okay, let's plug in our bounds. This is big R cubed over 3 sine phi minus 0. That's d phi d theta. Let's integrate with respect to phi. 0 to 2 pi. Integral of sine phi is negative cosine phi. Negative R cubed over 3 cosine phi. Phi goes from 0 to pi. D theta. Cosine of pi is -1, so I get positive r cubed over 3 minus a negative is positive, cosine of 0 is +1. So I have plus r squared over 3 d theta. So that's 2/3 r cubed over 3. I think I said r squared a second ago. Okay, and then integrating with respect to theta is 2/3 r cubed theta. Theta goes from 0 to 2 pi. Plugging in bounds there, I get 4/3 pi r cubed again. Okay, so this probably the same difficulty as the disk method, maybe a little bit harder in my opinion, just because I mean, once you have this memorized, it's fine, but it does feel like a little bit too much machinery maybe for this problem that you could have solved 2 courses ago using the disk method, which is my personal favorite way to solve this problem. It's very, very short and simple. Okay. Next videos will have more examples of spherical coordinates, and those examples will be ones where you have no choice other than to integrate in spherical coordinates. And yeah, as I said, that's the one that's the most different from what you've done before, and so it's the one that'll take more practice, and it's the one that we'll spend the most time on.